Hi. In this chapter, we'll cover the basic electrical circuit laws. We will start out by talking about resistance and move to Ohm's law. From Ohm's law, we'll talk about resistors in series and parallel. Additionally, we will cover Kirchoff's laws. Kirchoff's laws include Kirchoff's voltage law and Kirchoff's current law. So let's get started on this chapter. We will start by discussing resistance. Resistance comes from the base word resist, meaning to stop. Right? Resist meaning to stop. So resistance. So if we talk about our example where we have water, remember this example with water, and then we have current flowing, right? This is the current. If we want to discuss resistance, we would have rocks in the water. So these are rocks. And these would be our resistors. The resistors block the flow. They stop the flow. So these are our resistors here. Now, discussing our resistance here, if you think of this as a resistor, and we draw resistors in this manner, this is how we would draw them in a circuit. But a resistor is made up of a certain amount of material. It's made of a material. And so the resistance R, is equal to this material property, the Greek letter rho, this is a Greek letter rho, times L here, over A. So big resistances stop a lot of flow of current. Small resistance let current go by quickly. So if we talk about resistance, it depends on the material and the length, how long this is, and the area. So a big area, if A is very big, then the resistance goes down. The resistance is if A is big. And likewise, if L is big, the resistance goes up if L is big. So it goes down if A is big, and the resistance goes up if L is big. Resistance is measured in ohms. So resistance is in ohms. And we write ohms as the symbol omega. So this is omega. We write the ohms as omega because they both have O. Ohms, omega. So if we talk about a battery, so this is a battery, and we have positive, negative, and we connect wires to here. and there's a gap in between here, R is equal to infinity. All right, this is what we call an open circuit. An open circuit where the resistance is infinity. Okay, now if we connect those wires, the current flows. And I becomes very big. So our resistance here is approximately 0. Very close to 0 if we connect a battery this way. Okay, so we have resistance being very big and resistance being very small as 0. Now let's take a look at Ohm's law. So Ohm's law. This is very important in this class. Ohm's law. We have V equals I times R. So what does this mean? If we have a resistor that has a resistance of R, and we know the current I, how fast it's flowing, the current I, we can then figure out the voltage across this resistor, and this is from plus to minus, positive, negative. So V equals I times R. V equals I times R. So if R is very big, if R becomes very big with I, the voltage is very big. And if R becomes very small, the voltage becomes small. So this relationship here is called Ohm's law. Okay, so now let's take a look at different resistances of different materials, So on the left here, we have different materials, and then we have their resistance. So we have silver, which is very expensive, costs a lot of money, and it has a very low resistance, meaning that electricity or electrons are going to flow very quickly through it. So we use silver in computers, parts to make sure that things are conductive. So we call things with very small resistances conductors. Copper, we find that in most of wires or electricity. Wires are made of copper. Aluminum is also a good conductor here. And gold, more expensive than silver. All of these are good conductors because they have very low resistance, very small. Okay? And then on the other side, we have things with very high resistances, very big. Okay, so glass, Teflon is a plastic. So Teflon's a plastic, and these have very high resistances. So they are very good at insulating, or now not allowing electricity to flow. So they stop electricity. And then in the middle here, we have things that are in the middle. They are not big, they are not small, just in the middle. And we use these materials for semiconductors. So depending on how we arrange these materials, we can get some very interesting properties out of these materials, which is a good thing when we're talking about computers, cell phones. All of those things are use semiconductors. Let's start by talking about Kirchoff's current law. Kirchoff's current law, sometimes called KCL. So, Kirchoff's current law. KCL. Okay, so let's say we have a node here. This is a node, and we have currents. We have I1, we have I2, and we have I3. So this states that a charge cannot build up at a node. So what goes in must come out. Okay, so we have something called, we set the in equal to the out for the current. So we're looking at current. So coming in, we have I1 plus I2 equals the out. So both of these are coming in. This one is going out. So we have I3. Now we can rearrange this equation for I1 plus I2 minus I3 equals 0. So these are the same thing. Whatever one you want to use, you can use. So these are the same thing, and that is Kirchoff's current law. Now let's move to Kirchoff's voltage law. So Kirchoff's voltage law. And Kirchoff's current law is KCL. Kirchoff's voltage law is KVL. Kirchoff's voltage law. And this one, let me draw this. So these are resistors. This is a resistor. This is a resistor. And we'll call this V2, V3. These are the voltages across each resistor. We'll call this V1. And this is V5. And this will be V4. 1, 2, 3, 4, 5. And what we're looking at here is the voltage around a loop. Okay, so if we start here and we go around all the way around this loop, we call this a loop. So that's a loop. And what we know is the voltage around the outside of this is equal to 0. Okay? So let's start right here. We're starting here. And if we go negative to positive, this direction, we say that's positive. So we have V1. So this is positive. Now we go negative or positive to negative, and that is then a negative value. So we have minus V2, and then we have another one, positive to negative, that's V3. So we have negative V3, And then we go to V4 here, and that's negative to positive, negative to positive. So that's a positive now, and that's V4. And then we have V5, which is positive to negative. And we set that equal to 0. Okay, so the voltages around a loop must equal 0. Must equal 0. And the signs that we use are this sign, this sign, this sign, this sign, and this sign. So it's positive, negative, negative, positive, negative. All right, so we have this here. And this is Kirchoff's voltage law. So two laws, Kirchoff's current law and Kirchoff's voltage law. Let's talk about resistors in series and resistors in parallel. So series and parallel. Let's take a look at this. So if we have the same current, we say that they are in series. For example, we have a voltage source and we have 3 resistors. 1, 2, 3. So this is V, and we have R1, R2, and R3. And R1, R2, and R3. We say that R1 is in series with R2, and R2 is in series with R1. But R1 is also in series with R3, and R2 is also in series with R3. So R1, R2, and R3 are all in series. Series. Are all in series. Because the current I1, I2, and I3, I1 equals I2, which equals I3. So they have the same current, or the equal current. I1 equals I2, which equals I3. So we say that they're in series. Now we can do several things with this. Let's say, let's erase this quick. We want to figure out the total resistance. So the total resistance. We can simplify this circuit. We have voltage here. And this is the equivalent resistance, Req, meaning equal. This is V. So we want the equivalent resistance. So Req is equal to R1 plus R2 plus R3. R1 plus R2 plus R3. This is the equivalent resistance. So adding all of these together, R1 plus R2 plus R3. Now, what if we want the voltage across resistance 3? We want this voltage, V3. What is that equal to? Well, to figure that out, we have an equation, R3 equals R1 plus R2 plus R3 times V, times this. And so if we want to figure out the voltage across R3, we use that resistance divided by the total resistance, the equivalent resistance, R1 plus R2 plus R3, times V, this value. And this is what we called voltage division. So dividing it. So taking apart. So taking a full thing and dividing it. So voltage division. This is voltage division. Now let's talk about parallel. So here we said equal current through resistors means series. Now we're going to talk about parallel. So parallel means same voltage or equal voltage. So this is parallel. And we say parallel can be written as two lines like this, meaning parallel lines. Parallel lines. So parallel lines meaning parallel. So if we draw a circuit, and we have a current source for current here, and we have R1 and R2. These two resistors are in parallel because they have the same voltage across them. So if we talk about the voltage, V1, V2, V1 equals V2. Same voltage, meaning that they're in parallel. Okay. So what if we want to add these resistors together? So if we add them together just to get one resistor, we want R equivalent. So if we add these together, how do we do that? Well, 1 over REQ equals 1 over R1 plus 1 over R2. So this is 1 divided by R1. Sometimes in English we say 1 over R1. 1 over R1. Over. 1 over R1, 1 over R2. Or 1 divided by R1 plus 1 divided by R2. And this is the equivalent resistance here. So this can be sometimes a little difficult because you need to add them up and then take the reciprocal of them. So we can rewrite this equation. REQ equals R1 times R2 divided by R1 plus R2. These are the same. These are the same. Same equation. So you can use this one or you can use this one. It's up to you. I like this one better because if you have more resistors, here, you can just add more onto here. So if you have more resistors over here somewhere, you can add on to this. Okay? So that is the equivalent resistance. Now, when things were in series, we had voltage division. In parallel, now we have current division. So if we look at I1 and I2, I1 goes through here, I2 here. So I1 is equal to R2 over R1 plus R2 times I, this I. So if we want the current I1, we use this resistor divided by this plus this. R2 divided by R1 plus R2. So we need to use the opposite resistor. And likewise, I2 would be R1 divided by R1 plus R2 times I. Okay? And this is what we call current division. So we're dividing the current. So we're taking one piece and we're dividing it. So current division. Current division. So now that is series and parallel.